Hi, everybody. Obviously, we don't have class today, and this is actually Sunday night, but we don't have class tomorrow. And I hope everybody's safe and happy and all those kinds of things. So, couple of things, and then we're actually going to roll into the critical thinking that we didn't have time for last week. This coming week, I will have a couple of labs for you to do and look on the lab site. So that's AST102L, and go to Canvas, and I will have some attachments and things for you. And what I prefer you doing is taking those and printing them out and then putting them in your notebook next chance you get. You know, if you can't do that for some reason, you can fill them out, send it back to me. But I would actually prefer you to put them in your notebook. It would just be a lot easier. So, and in fact, several of the things I'll send you are sitting printed up already in the lab or in the classroom at Morrison, but obviously we're not going to be there. So I will send out some of those things probably tomorrow morning sometime. So keep an eye out for that. And also, this can be watched just about any time before the next week's class. And that's why I've got it on the YouTube channel. And this is CMU Astronomy YouTube channel. So those of you that tell me the link it doesn't work, probably means you're not working at it real hard, because it's YouTube and it's a link to a YouTube channel. So anyway, hopefully they won't have any issues with that. So what we're going to be doing is we're going to talk about critical thinking. And so let me get the sharing up here. And hopefully we will get this. Come on. I love having double screens. It just means I can't figure things out in stereo. Okay, why is that? There we go. All right. So critical thinking and study skills. We didn't really have time for this last week. Oh, and by the way, I believe we now have 26 people in our class. So when you come to class a week from tomorrow, don't be surprised if every seat is taken. And we've cleared off some seats. It's nice that it's a popular class, but I will have to do some rethinking on our labs, because our labs are really geared for about 15 to 18 people, not 26. So we'll make it work. And I'm really glad everybody has joined and is a part of it. So what we're going to do is talk about critical thinking. So what is critical thinking? Well, this is kind of one of those things you get offline. Critical thinking is the process of actively and skillfully analyzing, evaluating, and synthesizing information to form reasoned judgments and solve problems. And this, again, is a continuation of that definition. Critical thinking is a vital skill for academic, professional, and personal success, fostering intellectual curiosity and effective communication. I thought that was kind of a cute thing with, you know, well, actually, it's supposed to be kind of Satan out there in the audience. You know, God told me that one of you is questioning their beliefs. But a lot of what critical thinking is, it's questioning assumptions, identifying biases. Now, this is huge. And the reason why it's huge is because very few people identify their own biases. And we'll talk about that here in just a moment. And considering different perspectives to arrive at well-supported conclusions. So, in other words, you don't just say, okay, I believe this is such and so, and I'm not going to look at any other options. You look at your own biases, and I am a conservative, so I tend to look at everything from a conservative bias. However, just so you're aware, when things happen that affect both sides of the American controversy going on right now, I often watch CNN, what used to be MSNBC, because I want to know the other side, not just what Fox News or some other conservative thing says. And I think it's very important to identify your bias and keep an open mind to other options and alternatives. And so it's important to know those biases. It's also important to consider other perspectives outside of your own bias. And the reason that that's important is if you already make up your mind before you think about it, you're never going to come to any kind of different conclusion. And no one is ever going to change your mind about anything, even if it should be changed. So you also need it for shopping, ordering food, buying a house or car, and other daily tasks. So you use the scientific method or a critical thinking method for all of these things. And in fact, I suspect many of you are in this class because you did some critical thinking about what kind of gen ed science class you needed, and you decided that this is probably the best option for you for many different reasons. Some it's because it's this interesting sounding class, and some of you realize it's a lot easier than physics or biology or one of those kinds of class, or chemistry. And so we're going to talk again about some of that stuff as well. So here's some quotes. Thinking is not merely the rearranging of prejudices. William James. It is the mark of an educated mind to be able to entertain a thought without accepting it. Aristotle. That's another one of those things we do not see much of today in our modern digital communities. It's the idea that I would actually consider something I don't agree with and consider it seriously. I may not accept it. It may not change my mind, but I want to hear your viewpoint and I want to actually consider it with an unbiased viewpoint on my part. So the next one is the objective of education is to prepare the young to educate themselves throughout their lives. Robert Maynard Hutchins. So too often we give children's answers to remember rather than problems to solve. Roger Lewin. Knowing a great deal is not the same as being smart. Intelligence is not information alone, but also judgment. The manner in which information is collected and used, and that's Carl Sagan. And by the way, he actually has a book on critical thinking, and it's called The Demon-Haunted World. And the funny part is, I didn't agree with much of what he had in that book, but I've read it twice. I really found it to be very helpful for the thinking process. And then there is nothing more in common than common sense. Frank Lloyd Wright. I think that's a great one. So a discussion question. And of course, we really can't do that since you're going to be logging in whenever you have a chance to log in. So why is critical thinking more important in the 21st century than at any other time? And how would a person go about developing critical thinking skills? So I'm not going to give you those answers. And I will try to remember to ask you a week from tomorrow if you have answers to those two questions. Why is it more important in the 21st century than at any other time in history? And then how do you go about developing critical thinking skills? What kind of things do you need to do in order to do that? So first off, the first step is identify and define the problem. And yes, I did use AI for some of this, which again, this is the kind of stuff AI is good for. Clearly state the issue. Now, when I talked about biases, this is one of the areas that if you go in to identify the problem and you don't identify your own biases, then it's really hard to come to the right conclusion. I have a saying, and that is faulty premises lead to faulty conclusions. So if you base your argument on faulty premises, you will always come up with a faulty conclusion to your critical thinking. And I'm going to give you a specific example. Unfortunately, we had another terrible, tragic shooting in Minnesota. And again, this is not a political comment, but if you listen to all of the different media outlets and the pundits and the people talking, literally with less than 30 minutes after the shooting, two guys popped up on my YouTube feed that were already claiming that the police had no rights, or the federal agents had absolutely no rights to do any of this. They're breaking the Constitution, all of this. When you flipped over to another more conservative side, they're talking about how it's all legal and constitutional. So who's right? Well, that's where your biases come in. There's been several studies done recently, and I say that these are like news organizations, so they're not really scientific studies, about how people react to the different things happening, like with the George Floyd riots and with the LA riots last year, and now with what's happening in Minnesota. And what people come up with is whatever your bias is what people go with. So if you believe that there is no legal right for ICE or anybody else to be doing what they're doing, then you already have in your mind the way you're going to think about this. And if you think they do have a right, then you already know how you're going to think about this. So what the trick is not to approach it with your own bias, but to put your bias aside and say, so let me do some research and find out if ICE has a right to be doing what they're doing, or are they in violation of the law? And don't listen to all the talking heads and the noise out there. You have to determine that on your own as to whether it's correct or not. And the thing that's even making this whole situation in Minnesota so much more difficult is the fact that there's a huge scandal going on with billions of dollars in public money that have been lost. And there's actually, I think there's close to 90 people who've been indicted since 2022 on the whole subject. And so they're in court right now, and some of them have been found guilty of actual fleecing the government. So this is not something that one side is making up to make the other side look bad. This is something that's actually happening. And how do you know that? Well, you can go in and look at indictments and all of that. Those are the kinds of things that typically are accessible once they get to a court. So you have to understand what the issue is. If you don't know what the issue really is, how can you critically think about it? So what is the issue in Minnesota? Well, the biggest issue is, does the government have the right to do what they're doing? If they do, then you have to look at those facts. If they don't have the right, then you have to look at it from a different perspective. And I'm not going to answer that question because I'm not sure I really know either. But the bottom line is, until you understand your own bias, you get past your own bias, and you begin looking into the actual problem, and you state, and I'm going to give you the two problems that it could be, or a combination of both. One is the ICE Border Patrol has no right to be here. It is a constitutional violation. Or, yes, they are enforcing federal law. And the reason why this is so important is, if they are supposed to be there, and if they have a right to enforce federal law, then you actually have local officials who are saying that they shouldn't be there, but those local officials are actually breaking federal laws and aiding and abetting the felons. And if you have a situation where ICE truly does not have the right to be there, then you have a United States president and military and ICE and all that who are taking matters into their own hand and actually fulfilling what they are being accused of. So you have to look at this and you have to say, you know, this is how I feel. I don't like this. It's terrible. Okay, I get that. But you need to look at the problem and say, what exactly are they doing? And is this justified because of the law, or are they breaking the law? And you need to define the problem as to which it is. And once you define that problem, then when you gather information, you can sort out all the noise of all of the talking heads and everything, and you can actually understand the relevant facts and data to the situation. So then you have to, when you do these first two things, state the issue, gather information, and define the goal. What do you hope to achieve by solving this problem? So whether it's choosing what you're going to eat at a restaurant, or trying to solve who's at fault up in Minnesota, you have to define that goal and to understand why you're doing this and what you're doing it for. Just remember, the problem is never the problem. And let me repeat that. The problem is never the problem. I have been working with people in a community service role, either as a pastor of a church or as the head of a local food pantry, or working with a number of different churches in different communities. And one of the things that I have learned in over 50 years of doing this, oh, and also I have 7.5 years as a full-time teacher in high school. Or high school and 1 year in middle school, which was not my best year. And the one thing I've learned is the problem is never the problem. One time I had a student that never got their homework in. And I, instead of yelling at them or telling them they were doing a terrible job, I sat down and talked with them. And this was up at a Native American school. And I found out the guy had been kicked out of his home and he was living in a culvert under a bridge. And I'm not kidding. He actually was. I drove over there to see him. And that's why he wasn't getting his homework in. He had no paper. He had to borrow a pencil when he came to school. So I just sat down and talked to him. The problem wasn't he wasn't turning his homework in. The problem was he didn't have a place to live. He didn't have reliable light to work on homework after he got home from school. And one of the parents in the class heard about it, asked him to come and live there, and he became a straight A student. So the problem wasn't really the homework. The problem was something else. And I'm not saying it's always that clear cut. It isn't. But the problem is never the problem. What's happening in Minnesota is not really the problem. That is the focal point. And what the real problem is, you have to figure out. That's part of what you do with critical thinking. So I took a class from Delft University of Technology in the Netherlands. It was one of those free online massive classes. And it was on macro problem solving. In other words, big problems, not just little problems, but how to solve really big problems. And what we were assigned to do is figure out how to make green energy in the Netherlands, in a small country without a lot of natural resources. And everybody online in their online discussions were talking about, oh, we should do this, we should do that. And every time they did, they said, well, yeah, but this causes this problem. So you have this trade-off. If you put a coal-fired plant, that's not green. And if you put a nuclear plant, then you can have all these people upset because they don't want nuclear power. And if you put a bunch of windmills, you have farmers and other people that are upset because of that. And so you have to look at the entire problem, and you need to have solutions to every problem you're solving, plus solutions to the problems that the solving of those problems create. And one of the things they kept saying was, we don't do it the American way. And at first I was kind of offended. I don't get offended easy, but it's like, why do they keep saying that? And then they explained it. Americans are fantastic at problem solving. We will solve a problem. We're going to solve the greenhouse problem by making electric cars. That's going to do it. Well, the problem with that is there's not enough electricity. So how are you going to provide the electricity for all those electric cars? Okay, well, we're going to put up windmills. Well, you can't really have the best results from the windmills without some way to store the power. And every one of these solutions to that initial problem of making lots of electric cars has issues that actually harm the environment. A windmill takes like 25 years, which makes it near the end of its lifetime, to actually be able to be totally green, because the amount of greenhouse gases made making that windmill is astronomical. Same with cars. You have to drive at least 70 to 80,000 miles before it becomes what you call a green vehicle, because you have to make up for all of the greenhouse gases in production. And so we Americans, we have the problem solved. California was just going to ban cars, no problem, or ICE cars, internal combustion engines. And that was going to solve the problem. But they were closing down coal-fired power plants. And now they've gone from 40 oil refineries down to like 6. And gas is almost $9 a gallon there because of this. So it's okay to say you're going to solve the problem, but you need to solve all of the problem, not just one problem. And we Americans will solve that one problem, creating 5 more problems, but that's okay because we like to do problem solving. But in Europe, their way of solving problems is you've got to have a plan for all of the problems that you solve. And I actually got a pretty good grade in that class. I didn't get credit, but I just got the grade. I got a B, and I was pretty happy with that because it challenged the way I was actually thinking about critical thinking. And I had to learn a lot about how to do that. All right, so in analyzing and evaluate information, challenge assumptions, we already talked about that with biases. You have to question your own beliefs and biases as well as those of others. And very briefly, because I'm actually going too long with this, I actually am still a member of the Lexington, Missouri Police Department. And I have done ride-alongs, and I actually trained with the police in our department for several years. We'd go out to the shooting range, and I was like the second best shot of everybody there. So I have a bias. And my bias is I got to know those cops, and I went on rides with them. We were doing 100 miles an hour through a small town at 9 o'clock at night, just in the middle of a football game, because we were chasing a con who was driving a car and his license had been pulled. And when we finally got him pulled over, I mean, screaming through streets and all of that, the guy jumps out of his car and starts running towards the officer, who pulls out his gun and threatens to shoot him. And guess what my role was? I'm the chaplain, but when he got out of the car, he said, "Back me up." And so if that had gone bad and that guy had a gun, it changes how you look at everything. So I have a bias. I tend to be biased towards law enforcement and police. But in the Minnesota stuff, you can't go into it with that bias. You must question your own beliefs. Is what they did the correct way to do it? Is that the way you're trained to do it? And so it's important to know your own beliefs and biases and overcome them and be able to look at different viewpoints, which is the second one. Consider different viewpoints. Seek out alternative perspectives and interpretations. Ideally, if you were really interested in the subject of what's happening in Minnesota, go to your local police department, talk to the local chief, and ask him what he thinks about all these things and how they interpret it, and at least get their viewpoint. You know, you hear all the other people online very easily, but what do other cops think about this? Do they think those guys are doing what's right or wrong? And you could ask. So look for evidence. Evaluate the validity and reliability of the information that you're using. So you've got to understand, is this good information or bad information? When you talk about these things, you have to realize we have a glut of information, millions of threads online about some of this stuff. How do you know what's good and what's bad? And that's something that you'll begin to understand as you try to go through this process. And then look for logical fallacies. Be aware of common errors in reasoning that can lead to flawed conclusions. And one of the things that I have wondered about, and again, I'm not up there, I actually have a friend who is a news person, and they are going to Minneapolis this week. And I will look forward to actually talking to them because they're planning on going to where all of this stuff is happening since their news people have been reporting on it. And so anyway, I'm looking forward to being able to find out some things. But one of the logical fallacies you have to look for, one group says these are peaceful protests as people throw bricks, rocks, and have expensive gas masks. And then the other side says that they're not peaceful. And if you listen to one news outlet, they're all rioters. When you listen to another news outfit, they're all peaceful. I still remember from the George Floyd riots up in that area where a guy saying, well, the protests have been mainly peaceful. And in the background, there's people throwing things into this giant fire as a building burns down, kind of thinking that was not a peaceful protest. So the logical fallacy is, if you have to determine what is peaceful, what is the definition of peaceful? And then once you determine that, you have to determine, is this peaceful protest or not? And so these are some logical fallacies. A lot of times you can find some very easy common errors if you just think about it a little bit. Draw conclusions and reflect. So formulate logical conclusions. So you draw reasoned inferences, which means you take all this stuff and you put it together and you make an informed judgment. You consider the implications. Think about the potential consequences of your conclusions, both short-term and long-term, and then reflect on your thinking. So examine your own thought process and identify areas for improvement. How could I have done this better? Or do I still have biases that I'm acting on? And then communicate it effectively. Clearly explain your reasoning and conclusions to others. Very quickly, when you communicate, it's ideal to put the actual problem, what you did for your research, then what you did for your conclusion, and then finally, how you're going to tell people what your conclusion was and why it's important. So practice and seek feedback. This is number 4. This is kind of a sidelight, but it's true. So engage in activities that require critical thinking. If you go to the cafeteria to eat, that is an exercise in critical thinking. What do you want to eat today? But you can play strategy games, solve puzzles, and participate in debates. One of my other hobbies, of which I still kind of do, is I do military board games. These often recreate historical battles. And no, I'm not really into seeing thousands of people die. I was always into, could this battle have gone better and been over sooner and saved a lot more lives? And I still think about that. I haven't done it yet, but I've thought about scenarios in Ukraine, because right now, Ukrainians and the Russians are changing the face of land warfare and also ocean warfare and air warfare. So if you actually made a strategy game and played out scenarios, it might help to understand what's actually happening in that war right now. So ask questions. Don't be afraid to ask why and how to delve deeper into a topic. And sometimes sharing your conclusions with someone else and asking them, do you think this is a good idea or not? Do you think this is flawed? What did I miss? Those kinds of things. And then seek feedback from others. Ask trusted friends, mentors, or colleagues for their perspectives and suggestions, and realize not everybody's going to agree with you. Not everybody's going to think you're the most brilliant person on the planet. But even if they give you something you don't really want to hear, listen to it anyway and act on it. The next one is develop essential skills. Active listening, that's huge. Most of us, he included, would rather talk than actually listen. And that's not such a good idea. That's actually kind of a poor way to do it. Listen way more than what you talk. Research and information literacy. So learn how to find reliable sources and evaluate information critically. Again, the Tofflers in the 1970s stated that the main thing in the 21st century is learning how to parse good information from bad information. And so that's like a huge, huge issue. And then problem solving. Develop strategies for identifying, analyzing, and solving problems effectively. So I already mentioned this, green energy, turbines and EVs, government. I put atheists and young earthers, and that's just an area I have an interest in. I used to be a young earther, you know, Earth is like 10,000 years old, and I am not anymore. And one of the things I find is atheists and young earthers tend to be the least open-minded people. And both of them often claim that they're very open-minded. But if you present anything that goes against what their bias is, then they don't want to listen. And in fact, young earthers are told not to listen to anyone else's ideas or thinking. And I have, at one time, I actually had about 5 atheist friends. I'm down to 3 that I keep track of and have open dialogue with. And all of them, if you make a claim for some type of faith, they go crazy. And they don't want to listen. It's almost like they put their hands over their ears and go, blah, 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 blah. That is not critical thinking. And yet I've had atheists tell me, well, I'm a critical thinker and I just don't entertain this. No, you're not, because you're not listening to what anybody else says. You don't have to agree with them, but you ought to listen to them. So in science, the critical thinking is called the scientific method. We're going to go through this real fast because, again, I've already spent way too much time here. Typically, the scientific method is given in 6 to 7 steps, but you can boil it down to 4 steps. And this, to me, is the basis of my critical thinking. Observation. What do I see happening? Experiment. I'm going to experiment and find out if this observation that I made is correct or not. And then I have an evaluation. And the evaluation looks at the experiment and judges what result you get from the experiment. And then finally, you come up with a hypothesis or a new observation. Yes, the experiment supported what I thought. It didn't support what I thought. And so the evaluation is, well, the experiment was successful and my idea was wrong. So now I need a new idea. That's the nature of the scientific method. Now, I put a note to myself here, decision-making at McDonald's. And I think we talked about this the last time we had a class, which was like 2 weeks ago. You walk into a McDonald's and you look and you say, the McRib is on the menu. Then you decide you're going to eat a McRib. You haven't ever eaten one before, so you're going to give it a shot. You try it, and the evaluation is, I don't really like it. So the hypothesis is, I am not going to order a McRib sandwich. Now, I actually like McRibs. I don't know why. It kind of tastes like eating plastic meat, but I actually will order them when they're available. Go figure. I even ordered 2. They had 2 for the price of 1. And I ordered 2 of them and ate them both. I don't know what I was thinking. But anyway, so we use this observation, experiment, evaluation, hypothesis every day. And the critical thinking process is pretty much this process where you have a problem, you think about that problem, you state what the problem is, and then in lieu of the experiment, you begin to research, and then you evaluate your research, and then you come up with a new observation or a new hypothesis. All right, so that's the end of that particular sharing thing. And if you have any questions on this, send me an email. I'll be glad to answer emails. I will be traveling some this week. I have to go to Cameron on Tuesday, and I'm actually headed down in southern Missouri for the rest of the week after that. But I'm still working. So I would be glad to answer any questions you have, or if you want to know something about astronomy, let me know. I'd definitely love to answer that one. So let's go to the next one here, maybe. And let's see. Here we go. All right. This book, Planets in Perception, Telescopic Views and Interpretation, 1609 to 1909, by William Sheehan. That book is one of my all-time favorite books to read. I have several astronomy books that I really like. In this one, I've probably read 4 or 5 times. And it's very well written, has a lot of really interesting history. At least I think it's interesting. My wife thinks it's like the most boring stuff she's ever seen. But I also think her genealogy stuff is the most boring stuff I've ever seen. So we're even. And so I wanted to talk about this because telescopes are the reason why we know so much about astronomy. And I'm not sure that you can talk too much about telescopes in a modern astronomy class, because without telescopes, we would still think the Earth is the center of the universe, not just the solar system, but the universe. But it was because of telescopic observations that it was shown that we are not at the center of the universe, and that our planet is not even at the center of the solar system. So Galileo and his 20-power telescope. Somewhere I have a modern reproduction, kind of a 20-power telescope. The field of view is teeny tiny. And for an example, when Galileo looked at Jupiter, most of the field of view was taken up by Jupiter, which sounds really great. But Jupiter wasn't any bigger at 20 power in this telescope than it would be almost be in a modern pair of binoculars, except that it would be hard to find it because the field of view is so small. So I have a lot of respect for Galileo. He was able to take this newly invented instrument, build several kinds, improve them each time he did, and be able to do literal groundbreaking and record-breaking studies with it. First one to see the craters on the moon. First one to see the moons of Jupiter. First one to kind of see the rings of Saturn, though he wasn't sure what they were. And so this was a telescope with lots of aberrations, which means you look through a lens and it just doesn't look quite right. And yet Galileo did groundbreaking discoveries with it. This is what the telescope morphed into in a few short years in the 16 and 1700s. An extra long lens for single lens, larger aperture telescopes. I think I could use some commas in there someplace, in a space or two. But this is how they would actually do this. One of the things that was done, this one is using wood on top and bottom and then suspending it on a pole. And then people would look through that one end that you see down at the bottom right. And, it's 200 plus feet long, very small field of view, very hard to work. A slightest breeze would blow the lenses out of alignment and it would blur the image. So Christian Huygens had a 23-foot telescope. Now the longest, I think, was 275-foot telescope. But Huygens had a 23-foot telescope. That's as wide as a lot of, most rooms, like bedrooms in modern, just middle America, are 12-foot wide. And if you put two of those rooms together, that's how long the telescope was. And he did a pretty good job. The circle on the left shows what's called Syrtis Major. And then the other two, I forget exactly what they're called, but you can also see a polar cap in that center one. So the little round circle inside the circle at the top is actually Mars, is polar caps. So even with the 23-foot telescope that had a single lens at one end and another single lens at the other end, and it was that long so they could have some color correction, even with all that, he still was the first one to actually do a real sketch of Mars. And then there was Sir Isaac Newton. And for those of you who are science people, which I think there's only one in this class that's a science major, you can thank Newton for calculus and derivatives and all that fun stuff was something that Isaac Newton and a guy named Leibniz both came up with independently. And it's thought that Newton was slightly ahead of Leibniz, but each person had supporters who were arguing that their guy was first one to discover it. And it's likely it was Newton because he didn't think it was very interesting or important. And he just happened to give a paper on it 20 or 23, 25 years after he discovered it and was using it. And people went crazy because it solved so many problems in science. So the other thing he did is Sir Isaac Newton's reflecting telescope. So this is one of Newton's early telescopes. And at the bottom, you see an eyepiece towards the top of the telescope, and then towards the bottom of it, it looks like a little wind-up thing. Well, that is where the mirror is. And the mirror was made out of speculum metal, which is a combination of brass, silver, and I don't remember what else. And then you would literally polish that to the right surface and use it. The problem is every year or two, you'd have to repolish. You couldn't just, get some of the crud off the mirror. You actually had to repolish it, refigure it in order to make sure it stayed really good. I think I had mentioned 2 weeks ago that somebody found one of Newton's mirrors in a garage in England, or in a basement in England. And when they had it tested, it was very green because of all of the corrosion on it. But when they tested it, they found out it was just as accurate as any modern mirror, and that he did a fantastic job with figuring that mirror. This guy, Wilhelm Beer, and I always thought it was interesting. I don't drink, but I always thought it was interesting that Wilhelm Beer, who actually owned a brewing company, which may be where we get the term beer from, I do not know. He hired a guy. He was a very rich guy. He was a handsome, debonair, young businessman, had a beautiful wife. They were the belle of the ball, but he also was a very serious astronomer. He hired Johann Heinrich von Madler, who was an actual astronomer, had a doctorate in it. And he hired him to be his personal astronomer. And Beer was attracted by Madler's lectures. So Beer decided to set up his own observatory with Madler as the main observer. A 97 millimeter refractor was installed in a small dome in the Tiergarten near Beer's home in 1828. There, Madler and Beer began one of the more successful collaborations in the history of astronomy. And if I remember correctly, this was an early achromat, which had two lenses, which corrected for two different colors. And the reason why it's so significant is this map looks very much like the maps that came out of the 60s and 70s when NASA was charting the moon for moon landings. And when you look at the detail on this map, it looks very much like a modern map. And they didn't even use a 4-inch refractor. This is less than 4 inches to be able to do this work. So back in the day, before digital sensors and photographic plates, this is how everything had to be done. And this has to be one of the best maps ever made, especially with a small amateur-sized telescope. Beer also did drawings of Mars. These are very good. And the fact that he could do this much detail with a 97 millimeter telescope is pretty amazing. I have looked at Mars with a 6-inch refractor, which is much, I think it's be like 4 or 5 times the light gathering power of a 4-inch refractor. And I was not able to see this level of detail. And part of it was the location, but this was also in Germany. And Germany does not have the greatest skies for astronomy. The next guy up is William Herschel, or today, if he would be a rock star of science, and they'd be calling him Bill H. Hey, Billy H, man. But Herschel was a musician, and he actually didn't really want to go to war, and I don't blame him a bit. I actually have been shot at a couple of times inadvertently, and I can't imagine being in a battle where people are actively trying to kill me. One time there was a guy that was shooting a rifle at an old car, and it just so happened I was sitting on the car. And so the bullets start hitting the car right under where I'm sitting. And I went diving into bushes to get away from that. And then twice I have driven between policemen and criminals who are stealing drugs out of a doctor's office, and they are shooting at each other. And I didn't know that until I drove through the middle of it. And I happened to be in a convertible. So yeah, both times. And that was really interesting. So I don't blame Herschel at all for getting out of Germany during the 100 Years' War and going over to England, where he became a well-respected musician. But he got bored with doing music. He also was a guy who didn't sleep much. And I kind of resonate with that. If I get 6 hours a night, that's a long night for me. Normally I'm between probably 4.5 and 6 hours max, and very seldom ever get more than 6 hours sleep. So, I can identify with that. Well, he's found some books on math, and he began reading math. Now, math and music do go together. A lot of times people who are good musicians are also good mathematicians. And then he found a book on optics, and he got fascinated with it. And the next thing you know, he's borrowed a telescope, but he didn't like it. He thinks he can do better. So he begins building reflecting telescopes. And this is Herschel's 48-inch reflecting telescope. And you see there's a guy on the lift there. So you can see this is a very big telescope. And that whole A-frame looking thing is what's called an alt-azimuth, or an altitude and azimuth mount. And it would actually turn, and there's a series of levers. So you could pull the tube up and down. And you can see, if you look carefully, this is not the most detailed woodcut image here, but you can see that there's cables that go down into that blockhouse where they observed from. Or, sorry, not where they observed from, but where the base of it is. And so there's a cage on the front of that, and that's where the observing platform was. So you'd actually look at an eyepiece up there. Now, Herschel, though, did some really groundbreaking work with this telescope, but this one is the one that he did almost all his major sky surveys, and even finding Uranus. Uranus was found with this particular telescope. And this is a 9-foot telescope. No, the mirror is not 9 feet across, like we say today. Back then, they looked at the focal length, how long the focal length was. Because people from the very beginning have been fascinated with magnification in a telescope. And it was no different back then. So a 9-foot would have a lot more magnification than you would have with a 4-foot telescope today. It'd be a lot less magnification at 4 feet than it was at 9. The longer the focal length, the higher the magnification. And so this telescope is one that was his workhorse. And it had wheels on the bottom. So it would actually go up and down, but then you would turn it from side to side when you needed to follow an object. So why did Herschel use a reflector instead of a refractor? Well, the real simple reason is because refractors at that point weren't very good, but reflectors could be made to where they had equivalent to a modern day reflector, not only in reflectance, but also in the quality of the optics. So this is chromatic aberration. You have a single lens like what Galileo had. And the single lens, you see the blue, green, and red. The images don't come to the same focus. And part of the reason for that is because when light passes through a medium like glass, the different wavelengths of light slow differently. So if glass was, with light was reflected by glass evenly on all the wavelengths, it would be fine. Everything would come to focus, but it doesn't. The blue is bent more, it slows more than the red does. And so that is called chromatic aberration. In our big telescope, which you haven't had a chance to look through because it's not working right now, but in our big telescope, around bright objects like bright stars, many of you will see a purple halo around that star. Some people find it annoying. I don't see blue well. We've talked about that. I tend to see red better than blue. And then some of you are going to see blue better than red, and some of you probably just not going to be able to see very good at all because it's kind of the way it is. Everybody has a different style, and I've often thought those of us that have really good eyes, and especially good night vision, probably were automatically, without our thinking about it, drawn towards astronomy because you could see things so much better. So this is John Dolan. And he was the developer of what's called the achromatic doublet. And this was a flint glass and a crown glass. Each of those glasses would have a different refractive index, and they would work together to bring 2 of the 3 colors into sharp focus. It's actually almost 2.5 because you really get deep blue and ultraviolet that are not focused, but blue, the less blue all the way down to red are in focus, and an achromatic doublet. This is a chart. I have a 60 millimeter refractor at home. It is an f11. So if you look over, you see 60 millimeter on the left, and you look at the focal ratios. F11 is the focal ratio, which means that the focal length is 11 times the diameter of the objective lens, and that's up at the front of the telescope. So if you look at that, it's a 4.66 index, which means that you don't have much color there. It looks pretty good. And you have Conradi standard and the Sedgwick Sandwood. Don't worry about that. But basically, it means you're not going to see much color when you look at a bright object. I also have somewhere, can't find it, a 60 millimeter f9, or I'm sorry, f8 refractor, and that's a 3.39. You do see some color around bright objects with that one. I also have a 90 millimeter refractor, so you look down the column, you have 90 millimeter, and it's an f9, and it shows 2.54 index, which you can filter out the deal. However, there is a way of using a grading, which we'll talk about in the next lectures on gratings and about spectra. But you can actually use a grading to look at a spectra of the star and figure out how good the chromatic or the color correction in the lens is. And even though it's supposed to be terrible, it turns out that's one of the best telescopes I have. And it turns out that the Chinese that made this telescope, when they first started making glass to make telescopes with, because at one time all the telescopes came out of Japan. And when they moved over to China to save money, and the Chinese began making telescopes and optics, they would just use whatever glass they could get. And some of the glass was high refractive index glass, which means there's certain chemicals and things in it that make it more color controlled. And there's modern glass now where you can have two elements and have almost complete color correction in a lens. Normally you have 3 lenses to get really good color correction, but for visual especially, you can do it with 2 lenses using special what's called extra dispersion glass. I also have 152 millimeter, and it is an f8, and if you look down there, it's a 133, and that means that 6-inch f8 equivalent, it's not great. If you look at it, you get unacceptable levels of chromatic aberration. But again, it actually isn't too bad. I've been able to enjoy that telescope now for over 20 years. And I kept reading about how terrible that was, but I didn't really notice anything. And again, I don't see it as well. This guy, Joseph von Fraunhofer, he died in his early 40s, but he was a genius when it came to this sort of thing. He was the developer of the optical spectroscope. And this is showing him demonstrating to a group of wealthy businessmen the spectroscope and how you could use it to determine elements in gases. And so this is actually a stamp commemorating the invention of the spectroscope. And these lines, the black lines, are called absorption lines. And then there's also emission lines. It doesn't really show on here, but these are showing different lines that Fraunhofer was able to discover using his telescope. He also built a much better than the first guy, a much better achromatic telescope. This is the Dorpat refractor. This is often called the first of the professional achromatic telescopes. It's still in use today. And I think it's a beautiful telescope. You know, may not work as well as the Keck telescope in Hawaii or something, but it's a beautiful telescope to look at, and I'm sure it'd be a lot of fun to use. Now, somehow I got these guys in there twice. All right, this is where Beer was able to take all of his sketches and make projections of Mars. Now, this guy, Giovanni Schiaparelli, was the father, you might say, of the great Martian Canal controversy. Now, I'm kind of thinking most of you don't know what the Martian Canal controversy was. And even if you did know about it, you probably don't wake up in the middle of the night thinking, gee, I wonder where that controversy came from. So Giovanni Schiaparelli was an Italian astronomer, and he was able to see canale on Mars. Now, the reason why we called it the Great Canal Controversy, canale is Italian for channels. And he believed these were natural channels that he saw on the surface of Mars. And so he did this sketch, which is a map, and it shows many of the features on Mars. And the naming is slightly different than what was named later. Some of them are the same, some are not. And he actually, when he actually was looking at the sun through bad filters and started to lose his eyesight. And so we'll talk about who took his place in just a moment. Alvin Clark and Sons. These are the makers of the Morrison refractor. So the old gentleman in the center there, Alvin Clark, was a photographer from the 1800s who took an interest in optics. And after grinding some lenses for experimental cameras, he decided to grind lenses to make telescopes. And in the starting about 1870 on through into the early 1900s, Alvin Clark and Sons were the makers of the vast majority of professional level achromatic telescopes. And I say achromatic, very few people were making anything but achromats during this time period, including you have Yerkes Observatory, which is a 40-inch refractor. Ours is 12 and a quarter. This is 40. It's much bigger. And it's the largest refractor in the world, and no one will probably ever top it because glass begins to droop. And unless somebody comes up with the Star Trek transparent aluminum, you're not going to make a lens bigger out of glass than 40 inches without it being able to sag. And maybe you could put some kind of controls to pull it or something, but you can make a huge mirror and not have any of those issues. So Percival Lowell decided to take up astronomy. He came from a very wealthy Boston family, and Lowell was what they call a polymath. He was interested in everything. He actually got bored with business. He made a ton of money in the family business, owned a whole bunch of industries and plants and banks in the Boston area, gave it all up, went to the Far East, wrote a series of books there, and he also took a 6-inch brass refracting telescope that he would use on clear nights to look at stars and planets. When Schiaparelli began to lose his eyesight, Lowell decided to take up the quest to find out if there is intelligent life on Mars. So Lowell was the actual guy who crafted the concept. They're not canale or channels. They're actually canals built by an intelligent race on Mars. So this is the Clark refractor dome. It's called the Clark refractor because it's a 24-inch refractor made by Alvin Clark and Sons in Flagstaff, Arizona. I have looked through this telescope numerous times. Kind of humorous. When I was a freshman in college, I was a college football player. I know it's hard to believe, but I was. And I was a redshirt freshman. We had a game on Saturday, or actually a scrimmage on Saturday, but I decided to go up to Lowell Observatory, and at the time I only had a bike. So I rode my bike up one of the steepest roads in Arizona to the observatory. And after the public night, there was a very pretty co-ed that was running the telescope with a male assistant, and I sweet-talked her into letting me stay and look at things. And so I stayed for another 2 hours, and we looked at all sorts of different objects. One of the objects that impressed me the most was not the planets and all that. It's what's called M57, and we'll talk about that later on. And since 2009, I've been studying the central star of M57, which is called Planetary Nebula. Central star is a dwarf, a white dwarf star, or a blue dwarf star, depends on how you look at it. And when I looked at it, I'd ask him to open up the aperture at the front. Lowell Observatory always felt like if looking at planets, you wanted to have about 12 inches of aperture, very much like our telescope at Morrison. And I had him open it up to 24 inches so we could get better resolution. And when I looked at M57, I saw a green ring. It looked very much like a smoke ring. And at the center was a bright purple star. Now, bright, I say. It's a 15th magnitude star. Your eye can only see down in great conditions to 6th magnitude. And each magnitude is 2.5 times dimmer than the one above it. So a 7th magnitude star is approximately 2.5 or 2.3 or something times dimmer than a 6th magnitude star. So we're talking a 15th magnitude star. But the telescope, it was a beautiful night, 7,000 feet, over 7,000 feet, no wind, no moon. It was incredible. And I remember it all looked like it was in 3 dimensions, even though I knew it couldn't be. But it almost looked like you could reach out and touch it. And I have been fascinated with white dwarf stars and planetary nebulas ever since. So this is Lowell, Percival Lowell. They called him Uncle Percy, not to his face, but behind his back. And we'll probably talk about him in a week or two because he was kind of groundbreaking in hiring females to do things in astronomy, though not very groundbreaking. And there was another guy who definitely was groundbreaking. But Lowell was observing through the Clark refractor, and this chair and that setup is still there. And I've never actually used this. They had a different way of doing it because this is kind of old and it's definitely a collector's kind of thing. But I have sat in that chair before. So that was pretty cool to sit in the same chair as Lowell. Now, this is Percival Lowell's Mars drawing, or one of his hundreds of Mars drawings. He saw double canals. Turns out, to the best way of looking at it, it's likely that between the conditions, the atmospheric conditions, having the telescope stop down to 12 inches instead of 24, and because of eye fatigue, that he was actually seeing the capillaries at the back of his optic nerves. And as he would see those, the brain wants order, so it was making them look like straight lines. Now, that's one explanation. There's several others as well, but I think it's the most logical one. Because Lowell also saw canals on Venus and Mercury. So it seems like it was more a physiological issue than it was equipment. Here is a map that he made. This is a much more modern map with modern features that you would see today in images taken by amateurs and professionals. And E.C. Slipher was the brother of V.M. Slipher. V.M. Slipher was the guy that you'll learn about next week, that he was the first one to notice that galaxies were flying away from the Earth. And Edwin Hubble used that information to hypothesize an expanding universe. So E.C. Slipher is not as well known unless you're a planetary scientist, but these are drawings that he made, and he was, by the time he died, the world's foremost expert on Mars. He also had been a Arizona state legislator, the mayor of Flagstaff, and one or two other things as well. He definitely didn't let the grass grow under his feet while he was an astronomer. Oh, and he and his brother both were from Missouri. How interesting is that? All right. In the late 1800s, our telescope was built in 1875. In about 1880-ish, new technologies and new results started happening. This telescope is the Yerkes telescope. It's the world's largest refractor. And it was developed and built, and then he was also the first director of Yerkes, George Ellery Hale. So George Ellery Hale was an interesting guy. He spoke 5 or 6 languages. He could talk fluently in most of the European languages. He spoke German, French. He also had mental issues, and I don't mean that like he was depressed. He actually saw things. Something that came out after he died was a little leprechaun figure. He would see that leprechaun and talk to him all the time. And the leprechaun would actually tell him that he was stupid and didn't know what he was talking about. So the telescopes that he helped build, which were the world's largest, the 40-inch, the 60-inch, the 100-inch, and the 200-inch, all of those telescopes were designed, not so much designed, but visualized by Hale and his leprechaun. How bizarre is that? People say science is boring. It's really not. And so Hale one time did what all rich guys were told to do. If you're having a problem and you're not getting relief in a mental institution, where you chop wood and drink lots of milk, that sort of thing, you would go to Europe and then the Middle East. He was actually present at the opening of King Tut's tomb and was friends with, the different people that were doing that. So he was just an interesting character, but he was also one of the most respected scientists of the late 1800s and early 1900s. So here are all of Hale's telescopes. On the left is Yerkes, and then you have the 60-inch, the 100-inch, and the 200-inch. And all of these were made not just for visual, though the first 2 you could do visual with. They were actually made with photography in mind. And when photography came along, it changed everything when it came to astronomy. Our eyes cannot integrate photos, so you can't stare at one spot and build up a signal on your retina. It just doesn't work that way, but a camera can do that. So you can get much more detailed images using a photographic sensor or plate, and a digital sensor picks up way more, and we will talk about that in the future. Edward Emerson Barnard, one of my favorite characters. There is some evidence that Barnard may have been the first one to see an actual crater on the surface of Mars. It's probably unlikely that he did, but the 40-inch Yerkes that he was using at the time visually actually is right on the edge of being able to resolve something as small as a large crater in the Martian landscape. And there are some things in his notes, and his notebook was lost for like 50 to 100 years. And when they found it, he never said he saw it, but he kind of intimated that he saw some roughness that he didn't have a good explanation for. And so he was probably one of the best visual observers in all astronomical history. Beer and Madler may have been in the same category, but Barnard actually wasn't an astronomer. He actually was a photographer and a reporter for a newspaper in Nashville, Tennessee. And then he found out that if you discovered a comet, you could get money. So he discovered 3 comets, built a house for he and his family, and people were so impressed with that, they offered him a job out at Lick Observatory, which is in California. And after he made a reputation for himself there and taught himself astronomy, go figure, he ended up getting a gig as an astronomer with the world's largest telescope at that time, and that was at Yerkes. He also, because he had a history of photography or a background of photography, was one of the first ones to successfully take pictures or images of the night sky. He did dark nebula, which are nebula that absorb light instead of reflecting light. And he also got images of the Milky Way. He was the first one to really get successful images of that. So again, this is the telescope he used, the 40-inch refractor at Yerkes Observatory. And this refractor had a dedicated camera. It had a dedicated spectra. It also had a dedicated micrometer to measure so they could get the size of objects. And so they built there at Yerkes an entire laboratory to make use of all these new instruments that were being put on telescopes. This is Yerkes today, and I love the blue. And I did kind of borrow that color for our observatory because I just think it's cool. It looks good. And actually, I will paint some other stuff blue sometime this spring just because I think it's cool. But anyway, so this is now, used to belong to the University of Chicago. They sold it to a consortium of nonprofits that had banded together to save Yerkes Observatory for $1. And they're in the middle of a $2 million rebuild of this telescope. When it gets done, it will not be a research class instrument like it used to be, but it will be fully automated so that you will just tell it what you want to look at. It will go find it, and you'll be able to look at it either with your eye or with a camera. So this is the Yerkes telescope with film plate attached. And what you do is that round thing there with kind of see a black box, and he's actually looking into the black box. There, much of the image would be spread onto the photographic plate, which goes into that black box, the rectangular box. And they were rectangular plate glass with silver nitrate solutions on it to absorb the light and change it from dark into light, or actually light into dark. And what he's doing there is there's a small mirror that will pick up the light of a star, and you would center a star in there, and using a handbox control, you would actually make the telescope track accurately. Nowadays, it's done with a secondary telescope that has a camera on it, and it just changes and keeps everything completely centered. Even I have two telescopes that will do that. The one out in the dome or our roll-off observatory also can do that. So these are images by Barnard that were taken, and at the time they were considered to be some of the best photographs of Mars ever taken. And this is another photograph with better technique by E.E. Barnard with a 40-inch refractor in 1909. And these, up until the 1960s, were probably the best images ever taken of Mars. Photographic plates are not sensitive enough to get instant images. And so you get a lot of blurring. And the fact that you can see this much detail is pretty amazing. Well, that all changed when Mariner 4 crossed in a flyby the surface of Mars. And this is the low resolution pictures you get. And each of these images, I don't remember what the specs, but it's like 400 by 400 dots or something, or maybe it's 1,000 by 1,000. I don't know. It's not very much. And yet you can see that these are way more detailed than anything you could get from the ground. And so when Mariner 4 went by, it changed everything. Suddenly, Earth-based telescopes were not very good instruments to study the planets. And we began sending, and I say we, human beings began sending lots of flybys and orbiters around different planets because it's hard to beat being close to something. These are some images I took. The one on the left was taken with a 4-inch refractor, 102 millimeter refractor. And the one on the right was taken with my 6-inch refractor, or 152 millimeter refractor. And these would be considered, if this would have been done in 1960, I would have been the world's foremost photographer. However, there's people out there, I know a guy in Iowa that takes 2 times better pictures than this. My friend Rick Hill, that I'll talk about quite a bit. Rick Hill takes amazing photographs of the planets, much better than anything I've ever taken. So this is just for fun. This is the 60 millimeter Mars project. I mentioned it last time or in our introductory remarks that telescopes like this are often considered to be paperweights, junk, trash, hobby killers, they call them, yada, yada, yada. So I saw a bunch of people talking about how bad these telescopes are, how nobody should own one. They should ban them from, blah, blah, blah. So just for the fun of it, I went on eBay, found a telescope that cost me $22 delivered. That included shipping. And I took the telescope, put it together because it, comes disassembled in a box. And I went out in one of the oppositions of Mars and did this one. Now, it's hard to see the detail on this. It didn't really work. But this is a watercolor. This is a watercolor pencil sketch. So you use a watercolor pencil, and then you use a super fine brush to brush out the details. This is pretty accurate to what I could see. And if you get it on a bigger monitor, you can see in the center that there's some objects, and there is some contrast markings, which are what they call the markings on Mars, contrast marking. And this ended up in a group of images and drawings that a guy put together and submitted to the NASA picture of the day. And mine made it onto that. So I actually have a drawing with a 60 millimeter refractor that actually made it to the NASA picture of the day, which is a really big honor for amateurs to get on the NASA picture of the day. So this is another 4-inch refractor, and this is a color camera. We now have, here at the college, we have a QHY camera that's probably 5 times better than the camera I used to do this. This is called the ZWO 120 or 120 MC. MC is monochromatic or monocolor, so it's a color camera. And the one that we have has better resolution, smaller pixels, much more detail you're going to be able to see. And I still think this is an amazing picture. It almost looks 3D. It looks like it's kind of coming out of the screen at you. All right, so this is me 60 years ago. I was I think in middle school, and I was a total nerd. This is my 60 millimeter Sears refractor. And I loved this telescope. I looked at everything with this telescope. I also looked at the sun with a bad filter that I could have cracked and probably blinded me for life. Luckily, that didn't happen. And by the way, my mom made me those shorts, and my wife thinks they were the most hideous things she's ever seen. She's right, they are. But at the time, they were cool, and that's what everybody wore. Yeah, go figure. All right, so this is a telescope that I used for years, the Wright 28 Schmidt-Cassegrain. A guy named Paul Wright donated this to the American Association of Variable Star Observers. And for years, it was used at a remote site where you could log in, or actually not log in. You tell what you wanted to look at, and the guy that ran this, Tom Krejci, would actually set this telescope to gather data all night, and then you could upload it to your computer the next day. And I ended up getting this telescope, and the mount that's on it, it's called the Celestron CGE mount. It's pretty old, but they work really, really well. And it was made in I think about 2000. And so it's 25 years old and still going strong. But anyway, so this is one of the ones I used. I now have a 10-inch Meade on it. And then this one is my all-time favorite telescope. This is my 6-inch refractor I call the Beast. There's a guy named David Levy who has a doctorate in literature, and he did his doctorate on astronomy poems and writings. And he also was the co-discoverer of the comet that crashed into Jupiter back in the 90s. So he's a guy that's made a living out of astronomy, but is still considered an amateur. He's written a bunch of books and everything, but he names all his telescopes. He has one called Minerva, and I don't remember. He has all these really great names. So I had Little Eyes, the Beast. This is the Beast. And my favorite is the Bargain Bucket, which is a crappy looking telescope that still works really well after almost 40 years. And I built it myself. So I don't use it much anymore, but it still works. And It's gone through 3 renovations, and it does have world-class optics on it. Go figure. Because people look at it and go, that's like the worst telescope I've ever seen. It's like, yeah, I agree with you, but it works, so who cares? So anyway, I just did that to kind of make fun of David Levy. So this is a blank screen. This is just something real quick, and we're going to go through some other things here. We still have like 10 or 20 slides left. I don't know. But on the left is a 200-inch photographic plate. So this from the Palomar telescope, which is the world's largest telescope for like 40 years. And on the right is an 8-inch digital image. Now, the picture on the left is much better looking. I get that. But that's not what you're looking for here. If you can get past the weird looking stars because the telescope wasn't tracking accurately and all that, you will actually see that you can see as many or more stars over on the right-hand side through an 8-inch digital telescope than you can a photographic plate. And here's the difference. Photographic plate, back when this was done in the 1950s, if you could get 10% of the light to register on that plate in the form of an image, you are very, very fortunate. On the right, the digital sensor that took this picture was 92%. So if you have 100 photons falling on a sensor, 92 of them get registered. Whereas the other one, you have 10 photons that register, not 92. So the 8-inch telescope with a digital camera is almost as good or better than a 200-inch telescope. And now, if you put a digital camera on the 200-inch, then it becomes even more efficient. But you notice that there's 4 stars going through the image in the Horsehead Nebula. You don't see those stars with photography. So the digital was able to pick up fainter stars than the photographic plate. So the photographic plate revolutionized astronomy, and so did the digital camera when it came out in the 1990s. Here's the 2 kinds of telescopes you have. On the left, the refractor, and on the right, you have a reflector. We'll talk more about this in an upcoming lab. Here is prime focus. The prime focus would be where you'd have a camera inside the tube recording. And then you have a Newtonian focus, which is on the side, up the top side of the telescope. And a Cassegrain is what a lot of our Schmidt-Cassegrain telescopes are. This is a large telescope mirror. Shows one of the primary mirrors of the European Southern Observatory, very large telescope. Now, interesting part is this is 8 meters. These mirrors are made out of borosilicate glass, which is a glass that doesn't expand or contract much as it heats and cools. And it's made in the football stadium at University of Arizona. A British guy who became a professor of optics at the University of Arizona came up with a way to put chunks of borosilicate glass in a mold, spin the mold at a low speed, and be able to cut years off the figuring time of a mirror. And so 8 meters, the reason why they make 8-meter mirrors is they can't fit anything bigger in there. There's not enough space. And could you make a bigger one? Yes. But what they've really done is there's 2 things. They either put 2 or 3 or 4 of these mirrors together to form one telescope, which is what you have in southern Arizona at the, was a very large telescope, whatever it is, on Mount Graham. Or you have small pieces of mirror that you fit together and have computer control to keep them pointed in the right direction. So on the left is the Palomar 5-meter reflector telescope. And then on the right is the Gemini North 8-meter telescope. And Gemini North has a larger area than the Palomar mirror, but it's a lot less massive. The reason why Palomar is so much bigger is they had to have all that support to hold the tons and tons of glass. But they made a thin mirror controlled by actuators underneath a thin mirror, and you don't have to have as much support for that. This is one of the 10-meter mirrors, and you notice that it's not round. There's actually these sections of glass that are formed together. In each section, there's 36 hexagonal sections, and each of those sections have hundreds of computer-controlled actuators that keep the mirror pointed in the right direction. This is Cerro Paranal, a mountain on the summit 2.7 kilometers above sea level in Chile's Atacama Desert. It's the site of the European Southern Observatory, very large telescope. 4 8-meter telescope buildings on the site, and those 8-meter telescopes can be turned into one giant interferometer, which means they combine the light of all 8 of them to give you the resolution of a telescope that is like 3/4 of a mile across. So you get a lot more detail. This is adaptive optics looking at Jupiter in infrared image. And they use infrared primarily because it's much easier to correct for the atmospheric aberrations using the longer wavelengths of light. These are charge coupled devices. This is what's used to make cameras with. Your phone has one of these. They're CMOS, not CCDs. Or now they're calling them BSI, backside illumination, which is a way of, it's a CMOS that is more sensitive than the normal CMOS was. This is showing a guy in infrared, so you can actually see through the plastic bag. This is kind of cool looking. This is a prism spectrometer, and this is using a prism to make a spectra of a star or planet. This is a radio telescope. This is Jansky. We'll talk about that somewhere along the line. And Jansky was a guy that died, I think, when he was in his late 30s or early 40s. And it's unfortunate. He should have won the Nobel Prize for this discovery. But they never let him finish the study because all he was looking for was noise in the background of radio signals. And once they figured out what the noise was, they just filtered it out. So AT&T that he worked for didn't care about the science side, which is unfortunate. This is Cygnus A, and there's actually jets coming out of Cygnus A, and these are showing the jets shooting out of the center of this galaxy, which is where there's a black hole. And then these are areas where the high-speed jets are hitting and heating up gas and dust on the lobes of these jets. This is the Robert C. Byrd Green Bank Telescope, fully steerable radio telescope in West Virginia. And radio telescopes have to be much bigger because the radio waves, which are equivalent to light rays, they just happen to be at a different frequency, are much longer. And you actually can get waves in meters as opposed to thousandths of a second or even smaller, like a nanometer. And so they have to be really big in order to get any kind of resolution. Atacama, this is one of the latest. And the Atacama large millimeter, submillimeter array is in the Atacama Desert. This is near the other observatory. It is the world's driest location outside of Antarctica. And I think there's several places in this desert where there's not been any precipitation for at least 1,000 or 2 years, according to records. So this is a pretty good place to do astronomy. Oh, by the way, it's also at 16,000 feet, and this is the place that has a blockhouse to control all this that's pressurized. Because it's so high up, you just get stupid at 16,000 feet without either supplemental oxygen or being in a pressurized environment, like in a plane flying at 40,000 feet. This is very long baseline array, and this is showing where they actually combine all these radio telescopes into an interferometer. This is the largest radio and radar dish, the Arecibo. It has collapsed, and it's now been decommissioned, which is very unfortunate. However, the Chinese have something that looks almost exactly like this, and they've taken up the very large array kind of stuff that they were doing at Arecibo. There's actually the movie Contact has this featured in it, and then also GoldenEye, a James Bond movie from the 1990s, was featured in that movie. They showed the antagonist and the protagonist chasing each other through the center receiver out there. This Sophia has closed up recently as well. And now with all these telescopes above the atmosphere flying at 45,000 feet to get above the bulk of the water vapor for better observations, they closed this out so they could put the money towards other things that NASA could do, which is unfortunate. This did some really amazing work. This is the Hubble Ultra Deep Field. We'll talk more about that later. Now James Webb has one that puts this one to shame. These are some images from the James Webb Space Telescope. You've probably seen these, or at least some like it. And again, we'll talk about that later. Chandra X-ray, they just closed that one not too long ago, if I remember correctly. It's been around for almost 26 years, I think. This is the James Webb. This is the European extremely large telescope that they're building, 39.3 meters across. That's pretty amazing. And that, my friends, is all she wrote on this. So let me get out of this. Hopefully, on the laboratory canvas, your first lab assignment will be The Strange Tale of Barnard's Star. And again, what I prefer you do is print it out, fill out the stuff that's on it, which is critical thinking, by the way. So it's using Barnard's Star, which is a pretty interesting one, and actually making you do some critical thinking about Barnard's Star and then questions that you have to answer. Also, hopefully I can find it. I don't actually have I don't really want to drive to campus with, in fact, I can't. They did clean my driveway, so I can get out now. But yesterday and early this morning, I couldn't get out of my driveway. So anyway, I don't want to drive over just to get it since the campus is closed tomorrow anyway. So hopefully I've saved it on my cloud, and I will have an assignment of looking at the Pleiades. Now, here's the deal. If you can't do it, it's not the end of the world. But I want you to take a look at it, see if you can find the Pleiades, and they're very easy to find. If you go outside, put your face directly to the east, raise your chin to about 40 to 45 degrees above the ground, and you look straight ahead, you see something that looks very much like the Little Dipper. It's a Little Dipper. And that's actually the Seven Sisters of the Pleiades. It's not the Little Dipper constellation. Everybody gets that mixed up, but that's not it. And so there's just a little assignment to go out and take a look at that. And one of the things that will challenge you to do is, and I think it's one of the questions, but if not, what color are those stars? And a lot of times we have a tendency when we're just doing naked eye astronomy, we just go out and we just kind of go, oh yeah, really cool. And then we go back inside and watch TV. I want you to take a long enough look that you can try to figure out what colors you're seeing or not seeing. And there's something else you can do to enhance that. Most of the time we look directly at an object, but it turns out that's the least sensitive spot in your eyes, is directly at the center of your eyeball. So what I want you to do is look slightly to the right or to the left and not directly at the Pleiades, but look at them, look at something just to the right or the left, and then look towards where the Pleiades is and see if you see more color and detail. It's called averted viewing when you do this for astronomy. And averted vision sometimes allows you to see more detail and sometimes more color, not always. And not everybody can see color effectively. And if you are colorblind, just put that on the paper. Definitely not going to mark anything off because somebody can't see color. That's ridiculous. But anyway, so these are the two things that I will try to have for your lab work for this coming week. There'll also be a reading assignment I will put up tomorrow. Hopefully you've already done the last reading assignment. And that one, I haven't even looked to see who has done it, who hasn't. But that one is, there's 5 things that you have to put down for the 2 sections that you have to read. And I will take a look at those and give you points for them. And it's worth 10 points. So I think there's like 10 classes left. So that's 100 points because I'm going to try to make it, it'll either be 5 points or 10 points per reading assignment, just depending on what we do. So make sure you get those done. And I will definitely look forward to seeing you guys. It's really kind of a bummer to have to do it this way. One thing I learned from COVID is I would much rather be in person in a classroom than doing it online. I don't mind doing it online, but it's not nearly as interesting, I don't think. So I hope you guys have a great week. I hope you will be safe, and we'll see you in a week. Bye.